about the absorption phenomenon in a solid and typical semiconductors. The absorption constant can be since typically we have absorption in solid can be observed in this fashion. And then we have discussed about each absorption phenomenon. In a semiconductor. Okay. Today we are going to talk about the photoelectronic effect. Photoelectronic effect. Well, when the solid observes the light energies, then it has to give up their energy. And there are two ways to give up the energies. One is the radiative transition. And non-radiative transition. Radiative transition means we have photons, emit photons, and the typical example of this is luminescence. Right? So the give up energy, and this energy comes from the light absorption, and that is going to be the emitted photons, something like that. Non-radiative transition case, it has two ways for this, and Coulombic attractive center. And the other one is the so-called OJ electrons effect. To other free electrons. And this is called OJ electrons. And Coulombic attractive center is related to the imperfections. Say, if you have imperfection, and then the energy level can be described something like this. But in here, if you have energy like a staircase, the electrons with the excited by the light is give up the energy in this available energy state, something like this. In this case, we cannot have a high energies at once. You just give up the energies little by little, and then we can have phonons instead of photons. So it becomes non-radiative. We call that the non-radiative. So in this case, delta E is just N H bar omega phonon. It does not give up the energies very high at once. Typically, 1 electron volt energy will give up about 40 phonons released at room temperature. And the OJ electrons is nothing but when you have this is a conduction band and then the valence band. And if the excited electrons from the imperfections or the valence band, and when the light energy is stopped, then it'll give up the energies to lower lying energy levels. It can be imperfections energy level. Then this energies is going to excite the nearby electrons inside the conduction band. Okay, and then this is very low energies, and then it is going to be called OJ electrons. Okay, OJ electrons. This OJ electrons is energy of this OJ electrons is very low. So we have OJ electron microscopy, and with that, since the OJ electrons has a very low energy, it is very good for surface investigation. We have to use the OJ electrons. If you have a high energy electrons, like a SEM or something like that, then you're going to average out. The penetration depth is over 1 micron or so that the surface state really averaged out so that we cannot really see the surface of it. But the OJ electron has a very low energy so that it does not have the penetration depth of OJ electron is less than, say, 50 angstrom or so. Analyze the chemical composition of the solid only at the surface, 50 angstrom or so, then you have to use the OJ electron microscopy instead of other things. So this is a non-radiative transition, and radiative transition, this is our main concern. Okay, so next topic we're going to discuss is the recombination. Recombination. What happens in a solid? Now let's see. If this is a conduction band and a valence band, and then the excited electrons by the light, for example, is going to give up the energies by returning to the valence band directly, or this is going to be trapped in imperfections. And then if there is electrons in the imperfection, and then it is going to be refined, recombined to the conduction band, something like this, right? if you have an empty state here. All those recombination can happen to release the energies which has been given by the light, okay? So at steady state, the excitation rate should be equal to the recombination rate. Of course, otherwise you have accumulation or depletion of the electrons, which means it is not steady state. So the excitation rate or recombination rate can be given by N1, N2, beta 1, 2, something like this. This is the recombination rate. And N1 is the density of free carriers to be recombined. So in this diagram, we can see these are the N1, okay, and these are the N2. And this is the recombination rate. And N2 is density of a recombining site. Recombining site. And beta 1, 2 is recombination coefficient. Recombination coefficient. And it has a unit like the centimeter cube per sec. So something like that, okay? And this recombination coefficient is the cross-section, recombination cross-section multiplied by the thermal velocity of electrons. This is the average thermal velocity. Of electrons. And S12 is a cross section for capture. And the recombination beta 1, 2 values are known. We know the average thermal velocity is 10 to the 7th centimeter per sec. Okay, that is a typical number. And so the recombination coefficient, we have 3 cases for the recombination coefficient. The number 1 is a Coulombic attractive center. Attractive center and a neutral and a repulsion center. Okay, in each case we have a different recombination coefficient. And attractive center case, of course, it is the largest values we can have for this. 10 to the 5th. A neutral case, 10 to the 9th, minus 9th, and the repulsion case, we have 10 to the minus 14. So the recombination coefficient is so low in the repulsion case. In the repulsion case, we can draw the energy levels, which neutral case, we have recombination centers, something like that, something like this, the energy state. And for the attractive center, we can draw this energy levels something like this, okay? So the cross section is wider. And for the repulsion case, we can create a barrier here, something like this, okay? This is a repulsion case. And this is a attractive case. We can draw the energy structures around the different recombination centers just like that. So if you look into the details about the recombination, now here is the conduction band, and this is the valence band, and we have a thermal excitation rate, which is generally given, and then the recombination rate, something like this. This is the normal state, okay, in the dark, for say. And then if you have a light, h bar omega photons to this solid, then you're going to have new rate, or excitation rate, F, okay? So F is the excitation rate by light. Then this should be added to this. G is the thermal excitation rate, and R is the recombination rate. So at steady state, the GF should be equal to the R, okay? And we can set N naught and P naught is the concentration of electrons and holes in equilibrium, and delta N and the delta P is the increase in the free carriers by the light, okay? Density of free carriers increased by the light. Let's see, density of free carriers by light. And in a dark state, G, the thermal excitation rate, which is going to be equal to the recombination rate, of course, that is going to be N naught P naught beta from our previous discussion, we can see that this is the steady state excitation rate, which is equal to the recombination rate, of course. And if it is the intrinsic, then N naught is equal to P naught, so that this can be written as N naught square if this material is intrinsic. Intrinsic means it's pure, it is not doped. Okay? And in light, G has to added by F, and then that is going to be N naught plus delta N, and P naught plus delta P, and beta. And then in the intrinsic case, it should be N naught plus delta N square beta. All right? So that this is the N naught square plus 2 N naught delta N plus delta N square, and then beta. Okay? So that is F, the excitation rate by the light is going to be 2 N naught delta N beta, because the N naught square beta is going to be, it's going to be the G is equal to the G. Okay? I'm sorry. This, we can say up to here, and then we can distinguish two cases on this. One is the low light, which means the delta N is very much smaller than the N naught. Okay? So low signal case, low light signal case. And then we have this G plus F is equal to this, but delta N squared can be omitted. So that in this case, G plus F can be written as N naught squared plus 2 N naught delta N, and delta N squared, this can be neglected because it is small, and that should be multiplied with a beta like this, right? And then N naught square beta is equal to G, so that F now is 2 N naught delta N. Okay? Beta. And the delta N, from this, you rearrange this, F over 2 N naught beta. And by definition, delta N is equal to the excitation rate times the lifetime. This tower is going to be called photoconductivity lifetime. So from there, we can see that the tower, in a low signal case, the tower now is going to be equal to 1 over 2n naught beta in low signal. If you look at this equation, you can see that the lifetime for the photoconductivity is not a function of light intensity. Okay, its original population of electron is important in a low signal case. However, if you look into the high signal case where delta n is greater than n naught, then from this equation you can see that now F is equal to 2n naught delta n plus delta n square beta, right? The n naught square, now this time, this is a small value which can be neglected in this whole addition, summation. So only this two terms survive, and it is almost equal to the delta n square beta, all right? So delta n is now going to be F over beta, and the tau, which is delta n over F, and that is going to be F over beta F, and 1 over F beta. Now it is going to be delta n square beta. So this time tau is going to be 1 over delta n beta, which means in high signal case, the lifetime for the photoconductivity, we want to have a long lifetime for the photoconductivity to get something out from the by applying the light to the solid, and that the lifetime now is inversely proportional to the light intensity. Delta n is a light intensity. Okay, so if once you have a high signal case, then the photoconductivity is proportional to the inversely proportional to the light intensity in this fashion. Okay, so in the low signal and high signal case, it shows a different behavior, right? Finally, we can talk about the optical spectra. Optical spectra. In this optical spectra, we have situation. We can take an example in many cases, different cases, but in the textbook, it has a case where the conduction band and valence band, and then inside this band gap, we have a localized defects, impurity levels, and this is the ground state of the impurity levels, and these are the excited states of the impurities, which locate inside the band gap. In this case, this is the band gap, EG, okay, and then there is some energy level from this ground state of the impurities and to the conduction band. This has to have a special meaning in that, so that we can set this energy corresponding to that gap is E sub 1, okay? And inside this, let's say this is the E prime. And those three energy levels are important in the absorption of the light, okay? With that, you can draw optical spectra in this case. And the optical spectra in the book, it has 1, 2, 3, 4, 5 optical spectra has been shown in the textbook. And the first one, optical spectra, is the absorption constant and H bar omega incident. The photon light on this. And then the next one, 2, 3, 4, and then we're going to draw the final one here. 1, 2, 3, 4, 5. Okay? And then if you have a incident light, you start with the low energies of incident light, then obviously E prime is the lowest value. So if your light intensity is energy of a light is less than E prime, then every light is going to passing through this material. But once it becomes the energy E prime, then absorption can happen. Then remember, for the absorption to happen, you have to have an electron to be excited, and you have to have an empty state for the excited electron can occupy, and then you have enough energies for the excitation. So if light energy is high enough to have E prime values over here, then what's going to happen is that suddenly you're going to have absorption. And then you can have some energy levels here, that is the E naught. Okay, let me draw it here. And then in between, this is the band gap, actually. Band gap, okay? In between E prime and the band gap, we have energy levels corresponding to the E1, okay? And then when your light intensity reaches the E1, then you're going to have a absorption by these by the exciting the electrons in the ground states of the impurities to the conduction band. So you're going to have flat absorption. You can excite the electrons higher lying energy levels in the conduction band of these impurities, so that you have a continuous absorption after E1 energies. And then when your light intensity, light energy is beyond the band gap, is very high beyond the band gap, then you're going to band transition happens to make the light absorbed in the solid. So that after this, you're going to have some absorption constant, which is corresponding to these figures. Okay, this is very much understandable. Now, the next thing, the y-axis is the conductivity. photoconductivity. Now in this case, the photoconduction, by this excitation, the electrons is just excited to the inside the impurities, not to the conduction band, or the electrons is not from the valence band to make the holes in the valence band, and that hole is a free carrier. But in this absorption case, none of this happened. It just the electrons in the ground state of the impurity is excited to just to the conduction band of the impurities, so that there's no conductivity increase. There's no free carrier increase in this case. But if the electrons in the valence band of the impurities is moving to excited to the conduction band, now you're going to have a free carriers generation. So after E1, you're going to have some increase in the conductivity, photoconductivity. And then band-to-band transition, you're going to increase the hole, and at the same time you're going to have increase, you are going to increase the electrons in the conduction band, so that the conductivity will goes up like this. And then it should go, the photoconductivity should go something like this. But this one is going to drop out like that, because if you have a high signal, strong light, then absorption constant is going to increase, okay? Absorption constant is going to increase. It means that every light energy is going to be absorbed at the skin. The penetration depth, in other words, penetration depth decrease, so that every absorption happens on the surface of the material. Then the lifetime of the photoconductivity is going to decrease, because it's overpopulated, you should say. And delta N is F times tau, and tau is decreased, so that the delta N is going to decrease. So the conductivity is going to decrease at high H bar omega. So that's why we have a decrease in this high energies of the photons. Now the next one is luminescence, extrinsic luminescence. And then the next one is the intrinsic luminescence. All right? Extrinsic luminescence is more or less the same thing to the absorption, because the observed energy is going to be released by the luminescence. So the extrinsic luminescence is going to be equal, almost equal to the absorption, the shape, I mean. Shape should be equal. And intrinsic case, we should not think about this impurities, so that only at after the band gap, the luminescence intensity can be drawn there. And then the final one is just the luminescence itself. And in this case, the x-axis is changed by h bar omega emitted, which means the luminescence energies. Okay? And then it has luminescence at the first E prime, and then band gap. So we are having just 2 peaks in here. So that's how you can see the optical spectra in a solid. Okay, in reality, you are going to have all different situations, like not like this. you may have no impurities. You may have impurities with different kinds, many impurities inside, and depending on the defects, you are going to have different colors and different absorption constant and different conductivity, all those things you can make. All right, so that is going to wrap up the optical properties of solid. And as a summary, we can see that the first observation, the picture that I just erased, the higher lying band absorption, that is alpha value is greater than 10 to the 5 per centimeter. Okay, and band edge the absorption direct transition case is the same to the absorption in the higher lying bands, and then that is proportional to the h bar omega photon minus band gap direct and square root of this. Okay, and in direct case, we have a less probability for the absorption, so that it's about the 10 to the second and fourth. And in this case, you're going to have h bar omega photon plus minus h bar omega phonon minus band gap indirect. Okay? And the next absorption phenomenon is the excitons. Exciton absorption. And then that has the hydrogenic model because only one electron is involved, coupled with the host by coulombic attraction, so that you can use the reduced mass for the equation, and then your Lindbergh energies minus 13.5 electron volts, the hydrogen ground states. Now, imperfection case, if you have a imperfection in your solid, the absorption constant can be written as optical cross-section times impurity for the recombining impurity densities. And here the absorption cross-section is in between 10 to the minus 15 to 10 to minus 17 centimeter square. All right? And then the rest-Strahlen absorption, we have discussed earlier of this class. The light frequency is equal to the phonon frequencies, is kind of a resonance phenomenon, and it is good for deduction of the binding energies and so forth, right? And lastly, we talk about the free carrier absorption, which is important in a metal case. Metal is very important, and we see that we have a skin effect. And in the discussion, the skin effect, we have talked about the irony. The total absorption means the total reflection, something like that. And it just can be understood in a sense in the light of the energy conservation. Okay. So far we have discussed about the optical properties, and we just reviewed the refractions in the first of this optical property chapter, and then we go for the reflections, and we set up the Schrödinger equation, and at the boundaries we want to get those wave equation continuous. And then we can see the reflection coefficient, okay? And then finally, absorptions with 3 conditions has to be met for the absorption to happen in a solid. And then with that, we can construct the optical spectra in a typical case of the solid. And you can find different cases, and then you just observe, measure the absorption constant and the photoconductivity and so forth. Then you see the band E prime value, E1 value, and even the band gap as well. Okay, that will be the all for the optical properties in chapter 8. And then next week on Monday, we start talking about the electrical properties of solid, which is the most important chapters in this whole class. All right? I'll see you on the next week then. Have a nice weekend.